Welcome everybody. Last video on wave optics. Now this video builds a bridge to our next chapter, quantum physics. And as I have decided to do these videos in English, this video will be in English as well. So and I call it X-ray optics. The German physicist Wilhelm Conrad Röntgen discovered the then called X-rays in 1895. And nowadays, at least in German-speaking countries, they are called Röntgenstrahlung in honor of Röntgen, but since this seems to be hard to pronounce, they are still called X-rays, as Röntgen called them initially in the English-speaking countries. And sometimes, even in English, it's called Bremsstrahlung. I'm going to elaborate on this a little later. And he actually won the first Nobel Prize for Physics in 1901 for this very, very important discovery. Now first we have a look at an X-ray tube that produces X-rays. We have a glass tube that is evacuated, and then here the wiring is simplified. So the engineering students, please forgive me. Here I have a hot cathode, simply a wolfram wire that is heated by this voltage here, about 6 volts of alternating voltage, and then by the Edison effect, as soon as it gets hot, it emits electrons. So I get a beam of electrons that are accelerated towards the anode, and here I have a very high voltage ranging between 25 up to 600 kilovolts. So 25 kilovolts, 25,000 volts up to 600,000 volts, denoted by U sub A. And so as to get a fine beam of electrons, I have here an electronic focusing device, the so-called Wenelt cylinder, which is of slightly more negative potential than here the cathode. And this simply focuses the electron beam. That's not very important here. The electrons get accelerated up to very high speeds, depending on this voltage or the potential difference here. And then they hit the anode, the target metal, which is this guy here. This can either consist of wolfram or molybdenum or copper, to name 3 of the most used materials. Here, this whole copper block actually is just for cooling, because only about 1% of the energy gets transformed into radiation and 99% heats up here the anode. And in bigger X-ray tubes, you have extra cooling devices with water cooling, for example, where water flows in and out. So here, this whole thing is simply for cooling. Okay, and before we go on, I show you how such a tube actually looks in real life. So this little device here is an X-ray tube. That's all. So here you see the data. That's actually an old X-ray tube of a local dentist. Here you see the maximal voltage is 70,000 volts. The maximal current in the tube is 12 milliampere. And I think this is the maximal time for which you can have these data. Otherwise the tube will get too hot or something gets destroyed. Inside this metal cylinder you have the hot cathode. You can't see it here. No. And around it is a focusing system that creates a thin electron beam. Then between here and here you have the voltage that accelerates the electrons. And then here you see this copper block. This is actually to transport off the heat, to cool. The actual target is in here. That's that gray metal plate. I don't know what the material exactly is. Definitely not copper, but maybe wolfram or molybdenum. I'm not sure. And if this is the path of the very fast electrons, then most of the radiation comes here outward. Okay, and most of the X-rays that are produced leave the tube here in a direction perpendicular to the path of the very fast electrons. And essentially 2 processes are important to understand the creation of these electromagnetic waves with a very short wavelength. Okay, the first process that leads to this continuous part of the curve, here we have the wavelength and the intensity of the Röntgen radiation, the X-rays. These very high energetic electrons bump into the atoms of this target metal here, and of course they are decelerated very hard. And whenever charges are accelerated, deceleration is also a negative acceleration, they radiate electromagnetic waves. And this is what happens here. And this process, of course, is continuous because we have a variety of different decelerations. So electromagnetic waves with a continuous wavelength are emitted. The minimal wavelength can be calculated using the so-called Duane-Hunt law. It is about 1.24 microvolt meters divided by this voltage here, by this potential difference. So for example, if I have a 100,000 volts, 100 kilovolts, this will give me a minimal wavelength of 12.4 picometers. Pico is 10 to the minus 12, so very, very short wavelength. This is the point where here this continuous spectrum begins, and this part is actually called Bremsstrahlung. Brems is the German word for to brake, to decelerate. In English it's called braking radiation. So this gives me this continuous part of this spectrum, a whole spectrum of X-rays. And then there are some very small peaks. This here is for molybdenum at about, I think, 50 kilovolts or something. For copper it looks slightly more difficult. And these peaks, with these we are working in the following experiment. What is used in medicinal diagnostics and imaging with X-rays is actually here, this continuous Bremsstrahlung or Brems braking radiation. What we are using for crystallography are these peaks here. They are called the characteristic X-ray radiation or characteristic X-ray lines, and they have very well-defined wavelength. And we have not enough knowledge about the atomic structure yet to explain them in detail, but in short, usually such electrons will bump into the outer electrons of an atom in this target here. But these high energetic electrons can make their way through and down to the lowest level electrons and eject them from the atoms. So from the lowest energy shell, which is called the K shell, such an electron can eject an electron of the atom, and then this vacant spot gets filled with another electron, either from the atom itself or from a free electron, and then these peaks here come up with a very well-defined wavelength. And because here the electrons go down to the K shell, these are called the K alpha and K beta lines. Here from the second energy level to the first, and here from the third energy level to the first. But as I said, we do not know enough about atomic structure yet to really go into any details here. And one of the applications of X-rays you all know, like in a CT, a computer tomography, you have X-rays and the image gets evaluated with the help of a computer. And because the X-rays are so high energetic and their wavelength is so short, they can go through your flesh and organs and tissues and only get absorbed by your bones with heavier nuclei inside them. And this gives you the typical X-ray pictures. Here's a famous one of the first X-ray pictures that Röntgen took of it is said that the hand of his wife with the ring, but I think on this picture it's someone else's hand. Doesn't matter, you clearly see the bones. Okay, now around 1910, two physicists named Bragg, actually they were father and son. William Lawrence Bragg was the son, William Henry Bragg, they both named William, was the father. He was called Lawrence, he was called Henry. They did the following. I don't know the exact English term, I call it rotating crystal method, in German Drehkristallmethode. I think it's also called oscillation method or oscillating method, I'm not sure. So, what did they do? They pointed an X-ray source at a crystal and analyzed the X-rays that were coming out of the crystal. Now, back in the day, an X-ray machine was a huge machine, not because the tubes were bigger, but the transformer and the electronics to produce here this high voltage was very huge, so it was kind of hard to rotate the X-ray tube itself, or the whole apparatus. So they simply rotated the crystal they wanted to analyze. So here we have an X-ray source, then some sort of blind to filter out a small beam, and this beam of X-rays is shot at a crystal. And this crystal here can be rotated, and connected with the crystal is a detector, a Geiger counter or Geiger-Müller counter, which detects on the one hand radioactive radiation, but also X-rays. Well, gamma radioactivity in X-rays is not so different actually. And it clicks whenever it registers X-rays. So, and here, this is important for later. If this crystal, for example, it could be a sodium chloride crystal, so simply cooking salt or table salt. If this angle here towards the beam, the infalling, the incident beam direction is theta, then here this reflected angle is theta, but here is also theta. So this angle here together, so this angle here is 2 theta. This will pop up in one of the formulas. And here you have the result, what the Braggs found out. Here is the intensity registered by this counter here, and here is the angle, the rotation angle. Measured is this angle. Actually it's 2 theta, but here we have the angle theta itself. And then this clearly is an interference curve. We have distinct maxima and we have minima. Now these minima, as opposed to optics, are not here. The intensity is not 0. This has various reasons, but one of the reasons is we have a whole spectrum of radiation which can be detected. Mostly it's this line here, I think, but we have this whole spectrum. And there are a lot of scattering processes going on, so it's nearly impossible to get 0 intensity. But nevertheless, they found out for the first time that here, if I shoot X-rays at a crystal, interference happens. And I have constructive interference and destructive interference. Now here at the angle 0, most of the X-rays come through, so I have a maximum to start with, and then the intensity goes down. And here I have destructive interference, a lot, not complete, but a lot, and then it goes up, and at an angle theta 1 I have my first maximum. These angles are called glancing angles, because if you look under these angles in this bare light, you could actually see the reflection. I think this is why they are called glancing angles, or in honor of the Braggs, these are called Bragg angles. And here, for example, we have 3 maxima at 3 different angles. And this was a pretty spectacular result at the time back then, because it was one of the first experiments that actually proved that inside this crystal there must be small, what we call now atoms or ions, where scattering can occur. Now we have a look at the famous condition that Bragg Jr. derived in 1912. This is the famous law of Bragg, or Bragg's law. As I said before, this here is the son, Lawrence Bragg, and not the father. Now, what happens in general when an X-ray, which is nothing but an electromagnetic wave of very short wavelength, hits an atom? Well, this is an electromagnetic wave. When this hits the electronic cloud around the nucleus, it moves the cloud. The electrons begin to oscillate in the same frequency that this X-ray forces on them, and they themselves become sources of the same radiation, which is in general scattered in all directions. So we have these spherical wave fronts here that go in all directions. And this happens at every atom or ion of this crystal here. This is very important to keep in mind to understand what's following. So here we have some crystal lattice planes, in German Netzebenen des Kristalls oder Ebenen des Kristalls. These are different atoms or ions, for example, sodium and chloride. They have not the same size, but that's not important for now. What is important, they are in a regular structure, and here the distance between those two planes is small d. Now here is a wave beam of an X-ray. Yeah, here is the oscillating electromagnetic field. I omitted that in the other wave beams, and then this process happens. This atom here becomes a secondary source of X-ray radiation, which goes into all directions. The same here, 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 and so on. And now we compare these two wave beams here. We assume that the incoming X-rays are coherent, and then here, if here is the angle theta, and I draw this perpendicular line, then here I have the same angle again. And now this here is our well-known triangle from wave optics. And as always, we assume these wave beams to be parallel, so Fraunhofer approximation. And then here this path difference is nothing but this length, which is d, times the sine of this angle theta. And the same here again. And now when these two wave beams meet at the distant detector here, then this second wave beam had to travel more than this here, these two orange pieces together. So the path difference between these two wave beams is 2 times d times sine of this angle here. And the same for these and these and these. We have a lot of these crystal lattice planes. Okay? And now by the same argument as for the diffraction grating in optics, we can write down a law for the angles under which we have a maximum, a peak of constructive interference, as we see here. And this is simply the path difference, which is 2 times this length here, so 2 times d times sine theta n, must be a natural multiple of the wavelength of this Röntgen radiation or X-ray radiation. So this is the formula that became famous as Bragg's law. The maximum of nth order in X-ray diffraction is seen under these angles that satisfy this equation. N is a natural number, not 0, because for theta equals 0, a lot of the radiation simply passes through the crystal, and we shouldn't talk about constructive interference so much, because a lot of radiation simply goes through, I think. Now the applications are very important. If for some reason this d here is known, the distance between two lattice planes, then of course I can use this here to determine the wavelength of my X-rays. For example, I measure theta 1, this angle here, the first glancing angle or first Bragg angle, and then I simply can calculate lambda as 2d times sine theta 1. And this, as we have seen, of course, depends on the voltage that creates the X-rays, but as a rule of thumb, you're in the picometers, like 10 to 100 picometers, 10 to the minus 12 meters. That's a good range for X-rays. Actually, this is very, very interesting. I can't go into any details in this video, but you should definitely look it up. The XFEL, the free electron laser that produces X-rays, coherent X-rays, so it's called a laser, X-ray laser. This can produce very, very intense beams of X-rays. So check it out, watch a video on the XFEL, it's very, very interesting. So, but now if I know the wavelength of my X-rays, like for example, I know that I'm working with this peak here, I know the exact wavelength, then it gets even more interesting because then I can analyze the crystal that I'm shooting at, and I can actually determine here this value of D. And this is called X-ray crystallography or spectroscopy. And you can actually use the X-rays to determine the crystal structure, and for their contributions to this new field of research in the 1910s and 20s, father and son Bragg actually received the Nobel Prize together. That was very, very unusual. And son Bragg was actually 25 years old at that time. He was the youngest recipient of a Nobel Prize in physics, I think, up till today. So a German physicist named Max von Laue used these ideas to determine the crystal structure of a solid crystal, for example, of zinc sulfide. I'll show you a picture of the diffraction pattern that you get when you shoot X-rays at such a whole crystal. And from analyzing the pattern where the maxima, those are the dark dots where the maxima lie, you can calculate how the crystal must look like. Of course, we can't go into any detail here. Actually, the Laue conditions are much more sophisticated than this condition here, but as I said, no more details here. Now a much better method, because here you need a whole crystal, and as you have seen, the pattern is somewhat complicated. Two physicists by the name of Debye and Scherrer, Peter Debye, Dutch physicist, and Paul Scherrer, a Swiss physicist, used the following method in 1915. They pulverized the crystals and put them in a tube, what you see here. Here you have an X-ray source. Here you have a round aperture that filters out a small beam of X-rays, and then you shoot this beam at this tube of pulverized crystals. I zoom in here. So inside of this tube there are many, many microcrystals, and at each microcrystal Bragg diffraction can happen. Now here, for example, if this crystal is oriented like that, and it happens to have the right angle for, say, the second maximum, Bragg maximum. So here is 2 theta 2. The 2 was explained before. So here we have theta 2, and here this whole angle is 2 theta 2. Then in this direction on my screen, I get a maximum of X-rays. So there would be a marking on my film. And now, because there are so many crystals that are oriented in any way, if this crystal has the right angle, then there will be another crystal which is slightly rotated but also has the same angle, 2 theta 2, and another one, and another one, and another one, and another one. So taken all together, I get a whole cone of maxima. Yeah, the second maximum lies on a cone. And if I intersect this cone with the screen here, the screen is arranged in the form of a circle around this sample here, this tube. And if I intersect such a cone with this screen, I end up with circles. Maybe here I get a full circle for the first cone if it's small enough to fit on my screen. And then here the radii become larger and I only get parts of circles. But this is what I see on the screen. And this can be evaluated very easily. So this is the Debye-Scherrer method using microcrystals or pulverized crystals for doing X-ray diffraction. So here's a little example. We take a nickel crystal, we take X-rays of wavelength 50 picometers. The distance between here and the screen are 70 centimeters, and the radius of the second maximum ring is 20.5 centimeters. A is the distance between here, this sample, and the screen. This means large distance between them. Then by Bragg's law we have 2d sine theta 2, because I take the second ring, is 2 times lambda. I simply plug in n equals 2 in this equation here. And by trigonometry we have that the radius, this here, is a times the tangent of this angle, and here you must be careful not to forget the 2, as explained before. So this 2 has nothing to do with this. This 2 is always here for every maximum. Theta 1, theta 3, and so on. This 2 has simply geometrical reasons. And then you can solve these equations for d, the distance of the crystal lattice planes in my nickel crystal. Here lambda divided by sine of theta 2, and from this condition here I get theta 2 as 1/2 arctangent of R2 over A. If you plug in the numbers, you end up with 352 picometers, or 0.352 nanometers. And then you have gained information about this crystal. This is the beginning of this wide field of X-ray crystallography or spectroscopy. Okay, this should actually read spectroscopy. Of course, scientists took this steps further. In the 1940s, physicists or biophysicists started, I think Debye was one of the first scientists to do this, to do X-ray diffraction with DNA crystals. Biochemists, biophysicists were able to extract DNA into crystal structure, and then they shooted X-rays at it. I show you one of the patterns that emerged. And this actually led to the discovery of the double helix structure of the DNA molecule. It took about a little bit over 10 years. And now this is an interesting but also sad story. Here are some names that are intimately connected with this research. We have Wilkins, we have Rosalind Franklin, a woman, Linus Pauling, the famous Nobel laureate in chemistry, and Watson and Crick. They both received the Nobel Prize for doing the final steps of actually discovering this double helix structure. Now, as it turned out, they ripped off Rosalind Franklin pretty badly because they used her research without her knowing it in the first place. And they didn't even mention her in their Nobel laureate speech. And she actually died of cancer, I think, even before they got the Nobel Prize. So it's a very interesting piece of science history. If you're interested in that, you should definitely look that up and do a little research on your own. And that's it. That's all I had to say for wave optics. Now in the next chapter, this is why we did this in such detail, we are going to use this here. And it will turn out this is not only true for electromagnetic waves, but also for particle waves consisting of electrons or neutrons, whatever the hell that may mean. We are going to find out about that in the next chapter, quantum physics. Hope to see you there. Thanks for watching. Bye-bye.